as you can imagine, it is about gravity in many different ways. So the beauty of falling, in some sense, is the beauty of gravity itself and some of its universal nature. It's also the beauty of falling in the sense almost of failing, or in many different ways. In the fall, in the sense of letting yourself go, the beauty of embracing what is to come, and some sense the beauty of the space-time, just taking that and embracing it. But also, a lot of us may think of falling in some sort as failing, maybe, and it shouldn't be, but there is in gravity an element of the theory we have to describe gravity at the moment, the best theory, possibly the best theory that ever existed, which is Einstein's theory of general relativity. I think one of the reasons it is so perfect is because it predicts its own failure. So it predicts its own falls, if you were, its own pitfalls. And that in itself, it's really extremely profound, because it allows you to know when there is something else to uncover. It really provides you some sort of a window for opportunities for the future. So the beauty of falling is also in understanding that when you fall, there's something else to embrace coming afterwards. And that's where I'm coming from. So many failures in my life. I've fallen down many, many times. And it's not enjoyable. The fall itself is definitely not enjoyable, but it is an opportunity. And so it's embracing this opportunity for the future.
So do we really need a particle to mediate?
That's a really good question. So one thing that, whether or not we want to think of the particle, there is very much this element, and I think it's some sort of broadcasted to some level, that gravity is unlike the other forces of nature, that it's not a force, it's more the realization, the materialization almost of the curvature of space-time in which you find yourself. That's how you feel this notion of gravity, but it's really the curvature of space and time unified around yourself. And that is definitely true. It's an outstanding way to understand gravity and the way it acts on us and the way we act on it, and this sort of dance we have with gravity. But we also know that it's much more profound than that, and we know it's not even theoretical. We have observed gravitational waves. Those are great waves of gravity. We call them gravitational waves. On Earth, there's some another notion of gravity waves. That's not what I'm talking about. I'm really talking about gravitational waves, which are sort of this life of the curvature of space and time themselves. And they are very much the analog to light. So if you think of the electromagnetic force, this is mediated by, at the particle level, by a photon, but you can have more electromagnetic waves. You can think of it as a lot of these quantum of photon will make up electromagnetic wave at the classical level, and that's just a fancy way to say it's light. We do see light, and we do see this wave of the electromagnetic field. And the same is true for gravity. We have observed, we have felt those waves of the gravitational field. We have felt these waves of gravitational waves. And so there's a direct analogy there on how we understand and see light and understand it at how the propagation of the electromagnetic force is done at the more fundamental level by a fundamental particle, the photon. And so this analogy goes through all the way up to gravity and how we can think of it as the propagation of something more fundamental. I think maybe one of the questions underlying what you're asking is about the quantum nature of gravity itself. We have observed gravitational waves. That is a fact. But does it mean necessarily that there is such a thing as a graviton? Is gravity necessarily a quantized phenomenon, just like the other fundamental phenomenon of nature? And that's a very fair question. One of the things about gravity is that it connects everything. It has some sort of equivalence principle. So it connects connects with electrons, it connects with the light, it connects with itself, it connects with any system that exists. You put anything in space and time, like a mass if you want, and that will have an effect on gravity and create some curvature, and then through this curvature, that mass will then propagate in a different way in that space-time because it feels the curvature. It feels its own curvature. So there's some sense of back reaction. An object, a mass can have an effect on itself through back reaction of the space-time in which it lives in. And anything lives on the space-time. So any object, not only just a classical mass like a star, but even a more fundamental particle like the photon or the electron, which we know very, very well that they are quantum in nature, those have an effect on the structure of space-time. So gravity and the structure of space-time will back react on them. So if you have a quantum system, you should satisfy the quantum laws of probabilities. There are specific laws of probabilities. And those have to interact with other quantum systems. But we know that gravity connects with them. They interact with them. And so for the laws of quantum nature to make sense, in some sense to preserve the laws of probabilities, if you want the adding up probabilities for a phenomenon to happen, it should add up to 1 and not to something imaginary, not something complex or even negative or larger than 1. So for the laws of probabilities to make sense and to satisfy something which we call unitarity, so probabilities add up to 1, anything with which a quantum system interacts should also fundamentally be quantum in nature. And therefore, fundamentally, gravity has to be quantum in nature. There's no choice about it. Otherwise, all our laws of quantum mechanics and quantum field theory would just fall apart. So there should be a quantum nature of gravity, but that doesn't mean we have observed it. Symmetry, the very notion of symmetry is really fundamental in the way we think about everything at the more fundamental level. So the photon itself, the way we think about it is very based on symmetry, some sort of local symmetry. And there is a symmetry embedded in how we represent electromagnetism in itself. Now, gravity, independently of the other forces of nature, gravity, as described by Einstein's theory of general relativity, was very much set up under some of what we call Einstein pillars, which are very much based on symmetry. The equivalence principle itself shows that there's some level of symmetry being there, but more fundamentally understanding that any observer should see the same thing, should experience the same thing, should describe the laws of nature in the same way, independently of who you are, where you are, who you are, how fast you move, if you're around a black hole, if you're on Earth, or if you're in the middle of nowhere, that completely flat space-time. The way you describe the laws of nature should be the same. You shouldn't be observer-dependent, and you shouldn't matter on too much on your perspective. And so that calls for some notion of symmetry itself, which we call, the fancy way to call it is coordinate invariance or diffeomorphism invariance, nonlinear diffeomorphism invariance, but it's really telling you that you can be an observer and you can decide to describe the space-time with a particular notion of space and a particular notion of time, or you can be another observer and you have your own way of wanting to describe what is going on around you, and yet you should be equivalent. So that is, in some sense, a notion of symmetry. So this notion of symmetry is really rooted in the description of gravity in Einstein's theory of general relativity. So, yeah, I think you're absolutely right that the notion of symmetry and how to promote the symmetries we are allowing ourselves to think about is playing a crucial role on how we want to try to unify different phenomena together. So that was the case for the electric and magnetic force built into one framework, which is electromagnetism. The same was true once you brought in the weak force. It was embedded in something with its own symmetric group. And as you go on and include the strong force as well, you expect to go to a larger symmetric group, which is even higher level of symmetry. And then in the past century, for many years, people have thought about the idea of supersymmetry, which is an even higher symmetry group in a way to try to incorporate gravity with the other forces in a sense of supergravity. And it has made incredible progress. And actually string theory, which is one of the most remarkable possibilities for a theory of quantum gravity at the fundamental level, it is really based on a notion of supersymmetry. We needed to have an extended symmetric group to be able to describe strings in a way which would include gravity, include the other forces of nature, and much, much more. We'll get much more than that in the process.
I mean, status quo for 30 years is not a big status quo. Well, some things take thousands of years to get developed. I'm not suggesting it should take that long, but the theory I have been working with, which is not there to unify gravity with the other forces of nature, but was on a status quo for many, many decades, something like 8 decades. So, I mean, it does happen. I think in the case of unifying gravity with the other forces of nature, it is a little tricky in how to even formulate think about it. So we know, as I was saying, we know that as described by Einstein's theory of general relativity, the theory breaks down at some point. We know that because the theory would predict otherwise some observables, some quantities which could in principle be measured, if you're crazy enough to try, that would be as large as you want, even potentially infinite, and larger than the Planck scale, which is the scale of which you wouldn't even trust the classical result anymore, and quantum corrections would be in. And we know that happens, for instance, when you go very close to the center of black holes. As you go through the horizon of a black hole, that's all absolutely fine. You would die, and okay, but you would have your laws of physics, and you would have your Einstein theory of general relativity, which will still be completely valid as you cross the horizon of a black hole. You can go inside the black hole, go closer and closer to the center of the black hole, and it's only really when you get extremely close to the center of the black hole, then we know that the theory of Einstein theory of general relativity breaks down, because it gives us some curvature invariants which are way too big to make sense.
Yeah.
And the same thing happens if you go very close to the Big Bang singularity at the very beginning, very, very beginning of the universe, very early on. But in saying that, I'm talking about a point in space, and I'm talking about a time in the history of our universe, and I'm using words that I'm used to talking about space and time, because that's the way I think about it. We can't think so abstractly in a way that we don't even have space and we don't have a time. But when we say that GR, general relativity, breaks down, the very notion of space and time themselves have broken down. So I shouldn't even use those notions of space and those notion of time to try to ask myself the question of what happens. I'm trying to ask myself what happens as I get very close to the center of a black hole, but probably the notion of what I mean by that and where I am and what space and times are not the right way to think about it. And so I don't even know how to formulate the question. And by that, I don't mean me personally, but it's very hard to even appreciate how we should formulate more concretely the question. And so it's not surprising we don't have an answer. Most of the time in physics, being able to understand what is the right question to ask ourselves is 90% of the work. And then we can actually go about and answer that question. But we don't even know precisely how to formulate those questions. It's very tricky.